Hi, in this video I'm going to show you how to make attractive and accurate frequency response tests. And to start, let me start with a bad one. And here we are. I'll run this again just so you can note that this is really it. Let me pin it just in case. And it's noisy and it's sort of got bumps here and there, and the low frequency is kind of weird. And so, why is all of this bad? Well, to begin with, I'd like it to go to 50 kilohertz, and it's not even reaching that because 96 won't quite reach that. So, let me run it at 192K, and let's do that again. And what you'll see when I run it at 192 is it actually in some ways got worse. For one thing, the low frequency is really bad. That's because at 192.32, there isn't a lot of low frequency data. Now, in addition, let's take a look at a chirp for a second. And okay, here we go. Here's a chirp. And what a chirp is really nice because it goes through every single frequency in the range you want to test. But because of doing that, each frequency has very little energy. And so the trick with a chirp is making sure there is enough energy and enough of the data in the frequencies you want to get good results. And guess what? This isn't doing it. Increasing the size will give us a lot more energy and increase the resolution at the low end. So doing this will improve it. Let's do that. So now it's going to take almost a second, a little more than a half a second per scan. And so your time has gone up, but oh, look, the low frequency accuracy is way better. And the top end is now way up there. So that's all good. And now the big problem is I carefully set this to a tenth of a millivolt. Let's instead run this at a tenth of a volt. And we've now made a number of improvements to this, and we should start getting a pretty good result. And of course, it's a lot. There you go. All right, so we have improved to the chirp to the point where it seems like it's producing very good results. And again, let me turn off data point so it looks nice and smooth here. And let me go ahead and save the snapshot of this. I'm actually testing a preamplifier called apt-Holman. And so I have an apt-Holman preamp, and I'm trying to see how flat it is. And I've currently set it to flat. So here it is. Now, I'd also like to compare that to use turning the tone defeat off. So let me do that. I just flipped off the tone defeat, and let's run this. And I can compare the new result to the snapshot. And there we are, the snapshot, which is now in purple. And with the tone defeat, we've gotten noticeably better high-end response, which frankly, I can't hear, so I wouldn't care. And at the low end, actually, the match is virtually perfect. So that's the effect of a tone defeat. And actually, I'm going to snapshot that also. And we don't need to see the sweep frequency. Oh, actually, we do. Let's get rid of the voltage and the sampling. And now I can edit this stuff a little bit more easily because I want to rename this one to tone defeat. Okay. And now, because it's a preamp, I'd like to turn the bass and treble up and see what that does. So I'm going to turn off the tone defeat and start turning up the bass. And let's run and we can watch the bass go up as I turn it. And there we go. There's the bass all the way up. And I'm going to turn the treble all the way up. You can watch, but let's go ahead and just go ahead and save this like everything else. Snapshot this, and let's call this tone up. So we're getting a nice little story if we want to publish this for somebody. And let's do one last one, which is the tone down. And just for fun, again, we'll watch it. And I'll start turning the bass down. And I'm going to start turning the treble down. And honestly, that's pretty good. And so now I have the tone curves that represent the apt-Holman preamp, and they're rather good looking and publishable. So let's save this. I'll call it apt-Holman tones, which you can see I've done before. And just to prove that it's working, let's go ahead and load it. I do not want the configuration from there, but what about the data? And there it is. So that's how you do frequency response. Oh, before I forget, let's compare chirp to non-chirp just to get some feel for what this looks like. And the easiest way to do that is I'm going to turn the tone defeat back on and let's compare it to the tone defeat results. So we can turn off the flat and the tone up. And currently it's this purple, but let's turn chirp off and do a couple of these now. With no chirp, we don't need 128K. Let's run at 132K to be more speed efficient, as it were. And let's go ahead and run this. All right, so now here we are, 1 point at a time, and we can compare it. Now, what we see is that indeed at this frequency, for example, there was like about a 1 dB error at 11 hertz. And at, you can look over here at the cursor, at 17 hertz, the error is maybe a quarter of a dB, and then it's great. And here we are moving right along, and there's like perfect as expected. Now, when we get to the high end, we'll see what happens at the high frequencies. But as you can see, there's generally no reason not to use a chirp as long as you can run it at the parameters that make good sense for what you are trying to test. So how's this thing going to do at the high end? Look at that. It is matching the curve virtually perfectly, and it took way longer, and it has far less data, but it is a little bit more accurate, and that's worth something. And that's the end of the video.